rock. This session is on drill and blast method. As we learned earlier, drill and blast is another common method for hard rock excavation in tunneling and in mining.
The illustration on the right shows clearly the cyclic process in drill and blast underground excavation. Breaking the rock by blasting takes only seconds, but the whole cycle, from drilling to mucking and temporary supporting, takes several hours with modern equipment and machines. Usually, the maximum number of drill and blast cycle in tunneling is 3 times a day. The main activities in drill and blast excavation involves drilling the blast holes, charging and the explosives into the holes, set off the explosive to blast the rock. That is only halfway. We will then need to ventilate the working area to clear the air before scaling down any potential falling rocks. So mucking and the transportation crew can go in to remove the excavated rocks out. Often we will need to make sure the excavation working area is safe by installing temporary rock support using bolting and shotcreting. If drilling is not computerized, we will need to mark the positions of the holes on the excavation face manually. If we want to do joint mapping on the face, then this is done before drilling. Drill and blast can be done with full face or partial face excavation. When the excavation section is large, for example, for a cavern, they may involve partial or multiple excavation phases, including heading and benching. The drill and blast cycle process, however, is the same. The size of excavation phase is governed by several factors and needed to be considered the overall efficiency of the cyclic process. In general, small to medium size with area below 80 square meters, that is about 10 meter diameter, full face blasting is usually preferred. Excavation size often is also limited by the equipment used in excavation. For example, high height requires high scaling and rock supporting equipment to reach the roof. Let us move along the drill and blast cycle. Start with drilling and drilling equipment. Today, blast charge holes are drilled by powerful hydraulic drilling machines with tungsten carbide drilling bits. Compressed air drilling was invented for rock drilling in 1850s, made 5 meter a day advance rate. That was a remarkable achievement then. This made the old metal drill bits could not cope and need speedy and constant sharpening. Until 1945, tungsten carbide drilling bits have been used. In 1960s, pneumatic drilling machine was introduced. And in 1970s, hydraulic drilling was introduced and remains the main drilling method today. Since 1980s, computer-aided rock drilling started. The figures show here below are a modern drilling jumbo, the principle of drilling machine, and tungsten carbide drilling bits. Rock drilling today is very much automated and computerized. Modern advanced drilling equipment are computerized and automated hydraulic drilling jumbos. Computer can store drilling plans, and according to the plan, to position the drill holes. The drilling can be navigated by laser. Drilling performance has been increased from 5 meters an hour 100 years ago to 500 meters an hour today. With blast hole drilled, charging is to place explosives and detonators in the holes. Blasting is well designed in terms of time delay and the charging quantity. The figure here is the blast design of drilling and the charging of a rock tunnel. You can see the different charge densities for cut, stoping, and the contour, with contour being the lowest of only 0.4 kilograms explosives per meter. I will not cover the design of rock blasting. It is a rather different discipline, and you will need to be certified in blast engineering to handle explosives and blasting. Here, I will just illustrate some basic concepts in rock blasting and excavation. Blast is done in sequence, with time delay in blasting. It starts with cut blasting, usually around the center of the excavation phase. Then it is the stoping blasting, forming the main excavation. The final blasting is a contour to produce the final surface of the tunnel. There are several types of cut. The common one is the V cut shown below. There's always a lookout as demanded by the drilling operation. You need a bit of room from the wall to drill the hole. Blasting uses explosives. Before 1860s, black powder was used. In 1860s, dynamite was invented and used in hard rock tunneling. In 1955, AMPHO was introduced. That is the aluminum nitrate fuel oil. In 1960s, we started use water gel and slurries. And in 1980s, emulsion explosives developed and has been used in tunneling since the 1990s. Today, the common explosives used for rock excavation are AMPHO. It is cheap and bulk dosed, but sensitive to water. Emulsion is pumpable resistant to water, it is safe, and produce less toxic gases. Explosive gelatines are mainly used for smooth blasting. Explosive powders are getting less and less used. Explosion is generally initiated by detonators in rock blasting. Common detonators are electrical detonators, which was introduced in 1922, then with 1 second delay. In 1940s, short delay detonators of 10 to 100 milliseconds were used. Non-electrical detonators were developed in 1970s. Detonating cord are to be connecting all the initiation devices, as illustrated by the right figure. Blast can be instantaneous, millisecond delay, or long delay. For underground excavation in rocks, millisecond delay are commonly used. As I mentioned earlier, charge holes layout, charging, initiation, and the blast design are to be done by blast engineers. Blast engineers have tools to compute and design blast holes, charging, and the blast sequence. Nowadays, with powerful computers and 3D views, as the one shown on the right. As a rock engineer, if you wish to estimate the number of drill holes for blast, the equation in the box below gives the rule of thumb. For tunnels of small and medium size, full-face blasting is usually adopted. The Lochback base tunnel for railway use with a 10-meter diameter, that is about 80 square meter cross-section area. Full-face blasting in solid granite is adopted with a maximum advance rate of 60 meters a day. At the Godak base tunnel, also for railway, but in poor rock conditions, full-face blast was used for the tunnel with 10-meter diameter. However, face and roof pre-reinforcement, for example, by full pouring, were applied before excavation. After excavation, the tunnel was supported by steel sets and a shotcrete. For large excavation phase, such as cavern, blast excavations are done in heading and bench. As shown by the figure, drill and blast excavation of large cavern sections is divided into heading and several benching. Heading usually are done as top heading that allows to have the roof temporarily supported and safe for subsequent benching. The top heading in right illustration are done as a heading and reaming or side slashing. In terms of excavation cost, heading is always cost more than benching. Benching blasting can be done vertically and horizontally, as vertical benching and horizontal benching. Typical vertical benching is done for middle sections and most of the excavation where possible. It is generally the most economical way of rock excavation by blasting. Horizontal benching is suitable for creating a smooth tunnel invert. Here is an example of a heading and benching blasting for a large span cavern. The span is 30 meters. As you can see, pallet top heading was done first. With each advance of 5 meters, after each pallet heading advance, side slashing heading was followed. The two headings were done side by side. In some cases, they were alternated. After heading down, roof supports were installed, and then horizontal benching was done to excavate the invert. Blasting generates ground vibration. Blast vibration is considered as induced hazards, particularly if the blasting is done close to the built environment. The vibration leads to possible discomfort to human and leads to possible damage to existing structures. Blast vibrations are generally measured as peak particle velocity, PPV. PPV is used as a key parameter to assess building and structure damage due to blasting vibration. The table below is Australian standard, setting the recommended maximum PPV for building and structure damage control. After blasting, the next activity is ventilation. Ventilation is to bring fresh air into the excavation space to reduce harmful concentrations of CO, CO2, nitrogen oxides, and the dust produced by blasting. It can be done by pumping the fresh air into the excavation area and push the harmful air out, or by sucking the harmful air out, or a combination of both. This is illustrated by the figures below. Scaling is to bring down any potentially unstable rock blocks and wedges hanging on the roof and on the side walls, as illustrated by the drawing. Together with scaling, cleaning and preparing the rock surface are performed for shotcreting and bolting. Scaling can be done manually or by machines. The right figure shows scaling by machine. With ventilation and scaling down, excavation area is safe for the mucking crew to come to remove and transport the excavated broken rocks and the fragments out by LHD, trucks, locomotives, elevators, and conveyors. The choice of selecting different means of muck transportation depends on distance, efficiency, and economic scale. Environmental consideration can also be an important factor. For the Gotha Tunnel in Switzerland, due to the concern of local community, mucking was transported by a purposely built 3.2 kilometer long, 5 meter diameter mucking conveyor tunnel with a conveyor belt system of 3.7 km long, transporting 6 million tons of rock debris to a neighboring valley, without trucks passing through the villages. The marking conveyor tunnel with conveyor belt system is shown in the photo on left. The last two activities of a geoblast cycle shown in the illustration are installation of temporary supports of rock bolts and shotcrete, sometimes with wire mesh. Once the roof and the sidewalls are secured, we can then move on to the next geo and blast cycle. We will cover rock support, including temporary support, bolting and shotcreting, in a later session. This comes to the end of this session. We will continue with the next session on sequential excavation or Latin excavation. Goodbye and see you later.